Hey everyone, and welcome. I'm so glad you're joining us for this explainer. Today, we're stepping right into the hidden minefield of machine learning. You know, we constantly hear about the absolute magic of algorithms and their predictive power, right? But underneath every single slick futuristic model is a raw data set. And let me tell you, those data sets are literally loaded with traps. So we're going to walk through a complete survival guide to the life cycle of a model. We'll be uncovering the hidden, common mistakes that can completely wreck your data and ruin your analysis. To survive this minefield, we've got to start with kind of a guiding light. All models are wrong, but some are useful. This is a classic quote from statistician George Box way back in 1978, and it establishes right off the bat that no matter how advanced or complex or shiny an algorithm is, it fundamentally relies on an imperfect representation of reality. If we don't deeply understand those imperfections, well, we're just flying blind.
Okay, let's dive right into this. We're going to tackle this survival guide chronologically. First, we'll look at the illusion of perfect data during collection. Then, how we get trapped by our own brains during interpretation. Third, when math misleads you during the actual analysis. And finally, escaping the data traps to build your ultimate checklist.
All right, let's move into our first phase, the illusion of perfect data. This is all about navigating the hazards of data collection, focusing on the precise moment data is gathered, long before any math even enters the picture. See, there's this fundamental disconnect between reality and our data. Take meteor strikes, for example. The actual, literal number of meteor strikes hitting the Earth, that's reality. But the recorded number of strikes sitting in some database, that's just data. It's what we call the data-reality gap. Data never measures absolute truth. It only measures what human beings or our instruments actually manage to record. Think about it. If an instrument fails, or someone rounds a number, or a sensor is just placed in the wrong spot, boom. Your data has instantly diverged from reality.
And that gap? That leads to some incredibly dangerous sampling traps, like survivorship bias. There's a famous story from World War II. The military was looking at warplanes returning from battle, and these planes were just covered in bullet holes in very specific areas. Naturally, the military thought, hey, let's add armor to those heavily hit areas. But mathematician Abraham Wald pointed out the massive trap they were falling into. They were only looking at the planes that survived the selection process, the ones that actually made it back. The planes that got shot in the other areas, they didn't return at all. If a modern machine learning model had been trained purely on that surviving data, it would have confidently recommended reinforcing the exact wrong parts of the aircraft. No way you want that, right?
Another massive trap right at the collection level is the law of small numbers, or what statisticians just call N, the sample size. Look, if you flip a coin twice, getting 100% heads really isn't that shocking. Even 4 flips giving you 75% heads is totally normal. But scale that up to 2,000 flips, and it's going to stabilize right around 50%. The trap here is that small datasets produce wild, extreme results purely by chance. An ML practitioner looking at a tiny dataset might accidentally mistake that 100% or 75% noise for an actual predictive pattern. And that is a real game changer in the worst way.
Okay, so let's say you've safely collected your data. You've dodged all those collection traps. Welcome to phase 2, trapped by our own brains. This is where our own human cognitive flaws start playing tricks on us while we're trying to interpret things.
I want you to keep this massive number in your head for a second. 100,000. When someone gets a standard functional MRI scan of their brain, the machine is independently testing roughly 100,000 tiny volume units, which are called voxels, all at the exact same time, just to look for brain activity. Well, that massive number of tests is exactly what led to a real Ig Nobel Prize-winning study. This study enthusiastically concluded that a dead Atlantic salmon was actually engaging in emotional perspective-taking when it was shown pictures of humans. Now, come on, we have to ask, how on earth could a dead fish possibly show statistically significant brain activity?
It all comes down to this, the multiple comparisons problem. Let me demystify that dead salmon for you. In science, a result is often considered statistically significant if there's less than a 1 in 20 chance that it happened purely randomly. But remember those 100,000 voxels from earlier? If you test 100,000 things all at once, hunting for a 1 in 20 chance, the math practically guarantees that you're going to find around 5,000 completely fake, false positive, significant results. The salmon definitely wasn't thinking. The researchers were just testing so many variables that random noise eventually looked like a scientific breakthrough.
And this is exactly why you absolutely cannot just dump every possible variable into a machine learning model. Think about it. If you are building a model to predict lung cancer, using variables like age or smoking habits makes perfect logical sense. But if you just toss in random, completely irrelevant variables like how many movies someone watched or whether they own a dog, you drastically increase the chances of your model finding a fake, mathematically significant link. In the machine learning world, this is a trap called overfitting. That's where the algorithm blindly assumes dog ownership is a major medical risk factor just because it stumbled upon some random noise in the data. So this brings us to the third phase of our model's life cycle, when math misleads you. Because here's the thing, you can have incredibly clean data and a perfectly clear head, but the pure, objective math can still lead you right off a cliff. Probably the most famous mathematical trap is the post hoc fallacy. This is that incredibly dangerous assumption that simply because event A happened and then event B happened, well, event A must have caused event B. We've all heard the golden rule, right? Correlation does not equal causation. Yet, advanced machine learning models, which are literally designed from the ground up to hunt for correlations, get this wrong all the time. Take this hilarious spurious correlation discovered by Tyler Viggen. The data shows an almost mathematically perfect correlation between the divorce rate in the state of Maine and the per capita consumption of margarine. Literally, as margarine consumption drops, so do divorces. But obviously, one is not causing the other. Algorithms, however, don't have human common sense. They will gladly find these mathematically perfect relationships that have zero basis in reality and then happily base future predictions right on top of them. But sometimes, I have to say, these false correlations are deadly serious. Walk through this tragic timeline with me for a moment. Back in 1985, a massive observational study found that women taking estrogen replacement therapy had a lower risk of heart attacks. Because of that correlation, doctors prescribed it to millions of women for decades. But then, by 2002, actual clinical trials revealed that the therapy caused severe health risks. It's estimated that tens of thousands of women died prematurely. So what actually happened? It was a trap called a confound. Epidemiologists eventually realized that the women taking the therapy back in the 80s were generally wealthier, more educated, and they exercised more. Those were the hidden variables protecting their hearts, not the estrogen. The data just missed the confounds entirely. Then we have aggregation traps, like Simpson's paradox. This is a total mind-bender. It's a phenomenon where a really clear trend appears in separate, smaller groups of data, like, say, at a local county level. But that trend completely disappears or even totally reverses when you zoom out and combine all the data together at a state or national level. So if your machine learning model is extrapolating predictions from one level of aggregation to another, it might literally be predicting the exact opposite of reality. And finally, the ultimate mathematical trap, outdated models and invalid assumptions. The 2008 financial crash was heavily fueled by flawed value-at-risk models. These algorithms essentially assumed that the market operated on a predictable, normal distribution, a standard bell curve. But reality doesn't always look like a bell curve. Real markets are what we call fat-tailed, meaning extremely rare, catastrophic events are far more likely to happen than the basic math suggests. Relying on historical, normal data to predict totally unprecedented futures is a massive trap, and it literally brought down the global economy. All right, so how do we actually survive all this? Let's transition to our final empowering phase, escaping the data traps. It's time to equip you with the specific tools to defend your models in your analysis. Consider this your rapid-fire survival checklist. You need to be asking these questions every single time you look at a dataset. First, ask what is the N? Is the sample size large enough to actually trust, or is it just noise? Second, aggressively check for hidden confounds. What invisible variables might really be driving this trend? Third, if you're running thousands of tests, control for multiple comparisons so you don't get tricked by a dead salmon. And fourth, investigate the data collectors themselves. How was this actually recorded, and what bias did they bring to the table? So the absolutely crucial point I want to leave you with is this. We are living in a world that is increasingly run by predictive models, from deciding who gets a loan to making life-altering medical diagnoses. But data is not reality. It is merely a shadow of reality. So the next time an algorithm makes a decision for you, what reality is it missing? Keep asking that question, keep looking deeper into the algorithms shaping your world, and as always, stay curious. Thanks so much for joining me on this explainer.